Okay, so for those who are watching there or watching this afterwards, some of this won't work very well because I'm going to scribble various things on the blackboard as we go along as well. Maybe because I'm too lazy to put everything into my overheads because that involves me have to draw lots and lots of diagrams, and it's quicker to draw into the chalk than it is I get used to the chalk now. So anyway, yeah, as Mike said, I'm Dermot, this is Louise. We've been given today and tomorrow as our 2 days to talk to you guys about stuff. So what I reckoned today I was going to do is talk to you a bit about parallel I/O and how parallel I/O works, both from a system side of things in terms of building a parallel file system infrastructure and how the file system behaves itself, and then how do you engage with that as a programmer using the MPI/I/O layer to do some efficient reads and writes from your application, because I/O tends to always be the biggest problem. And then tomorrow, Louise is going to look at some sort of performance analysis things and some instrumenting and all those sort of things that you can do to your code to try and do some analysis of where your problems are in the way that your code is behaving. And also that will involve doing some messing around with compilers and linkers and how all of the various dynamic libraries and things like that work in programming in general. It's not specifically a HPC related thing, but it's, you know, it's one of these things that's important. I think if you're going to be a proper computational scientist who's meant to be good at doing this sort of stuff, these are the sorts of things you should know. So for today, you're mainly going to hear from me, but Louise will be able to answer some questions, and when we get to the sort of the lab sessions where people want to try out some various things, we'll both be around to answer questions on them. And then tomorrow, Louise will do most of the talking, and then also we'll have some examples of it. Well, I think so. We have the way kind of you've worked is sort of an hour or so here, and then break, and then kind of an hour or so of doing sort of labs and things so far. Is that kind of about right? Yeah. Okay. So I think today the first part of this is going to be more sort of theoretical, so there's not really going to be much we can do in the way of homework or lab work. So I think we'll probably go a little bit longer, sort of maybe until about 10:11 or so, talking through some things just to get you to the point of where we can do a few basic MPI/I/O things, then have a go after a break, have a go right some simple things, and then in the afternoon will probably be a little bit more, a lot more about the MPI/I/O stuff, and then sort of the afternoon then there'll be a few more things that you'll be able to do hopefully. So I'm going to let Louise sit down. She doesn't need to stand for the entire session. Just sort of, this is the next slide sort of demonstration. Okay, the other thing I should say is parts of this have been adapted / stolen from a presentation given by the guys from Argonne Lab last year. I think it was around sort of the structure of the parallel I/O systems. So like always, you should credit things that you steal things from. So why is it important for us to talk about parallel I/O and what's wrong with normal I/O? I suppose is the first question. Well, here's a Blue Gene machine, and you can see the size of it. And actually, this is quite an old Blue Gene at this stage. The Blue Gene now, you can tell by the very fancy slopey things that put them all together. People seen Blue Genes before, or at least sort of seen the diagram. They're actually really quite clever the way they're engineered. They've got all these low-powered CPUs engaged in these chassis, sort of, I think sort of 16 on each side of these line cards, soldered in onto a backplane, and then they have them set up with this sort of slopey cabinets, where basically they take in all the air here, and this is radiated such that the pressure along the side of here, the air pressure is constant, so that the air as it goes through the machine gets to every rack, every point in the rack at an equal pace. And then obviously there's a similar sort of venting system that sort of spits the hot air out the back, which is quite different from most normal HPC or even normal sort of computer equipment where the air comes up, gets sucked into the back, and then spat out the front. But usually means cold air is coming up from the bottom, which means all of these guys are much colder and all these guys up here are much hotter. Whereas when they designed the Blue Gene, they went, actually cooling is kind of an important thing, so they kind of built these slopes. Anyway, that's something to do with I/O. But the Blue Gene was quite a clever design even still, and certainly the current generations have a lot of the same sort of features. But the point about it is that they came with 4,096 cores in the Blue Gene now in a single rack, and then you bought 20 in that row, and 20 and 20, so you've got 60 or 80 or 100 racks of 4,000 cores all running MPI jobs. You're running tens to hundreds of thousands of MPI tasks, all trying to do one calculation together. And keeping those fed with data is kind of hard, because if you go back to this laptop here, or something of a single machine, the I/O capabilities of any individual machine is somewhere of the order of about 100 megabytes of data per second, is about what you can read on or off a hard disk, give or take. It's a bit faster if you've got an SSD, it's a bit slower if you've got an older spinning disk, but it's in and around that sort of space. And if you've got tens of thousands of CPUs all running at a number of gigahertz per second, and each of them can do 4 or 8 floating point operations per clock cycle, then you can see there's a massive imbalance between the performance between reading from a disk to get data into your computer. Obviously, if you build your algorithm such that you can kind of load in your data once and then just churn through all the data in memory repeatedly, then that becomes less of a problem. But for most computational HPC problems, I/O is a really big bottleneck, because you're constantly reading in new data, generating some interim results, writing them out to disk, generate some other things, doing a checkpoint in case your job fails. You're reading streaming data from some sort of sensor instrument you've got, a telescope or I don't know, whatever you might have. There's all these sort of applications that are there that are endlessly churning through the data. And so it's really impossible to feed tens or hundreds of or thousands of CPU, even tens actually, it's kind of hard, but certainly in the hundreds and thousands of CPU cores, you can't do this in a traditional serial manner. You can't just load up some data and then hand it out. And the other thing that we have to keep in mind about when we're talking about going from how we're going to do our I/O in the parallel world is that there's this disconnect between what we as programmers and modelers would like to see, where we have a complex data structure. Now this is some sort of mesh or something that's there for an airflow over a wing or some such computational thing. But you can see that is not a regular structure. It has all sorts of weird and wonderful things. It will have lists, binary trees, and multi-dimensional arrays, and all these sort of data structures that we have. And when we spit those out onto disk, the only model we have in traditional file systems is a linear set of ones and zeros. Right? There's no sort of multi-dimensional I/O that exists. So we need to have some sort of transformation from these complex structures to something that we can actually store on disk. And even as we've scaled up into big I/O systems, we've still kept this traditional model of, there's a file system. And so you have slash as the root of the thing, and then you have that feeds into maybe a slash home and a slash scratch or something. And then in slash home there'll be me, so I'll have my event, gfrost, and then there'll be user 2, and then there'll be some project, and there'll be some various projects under here. So you have your traditional file system is very laid back and it's very well defined, and within that then you have a file, and your file is just all of the data, and it's linear, it's sequential, and you start at the start and you finish at the finish. Okay, there's no way really easily to write one of these complicated data structures to disk and have it retain all of that structure. Okay, and so we need to be able to do some sort of mapping between these two to enable us to do some sort of level of speed up of these things, because we have to go from a very simple concept to a very complicated concept by the time we get around to doing our actual application. So the good news is a lot of this is being done. So you as the end user now can take advantage of work that everybody's already done. So that's good. But a lot of the time you'll end up having to modify what you want to do, because each of these models that are used to represent data is appropriate to your particular field. So how many people here are, let's say, mathematicians? Okay, not really. How many people are physicists? How many people are chemists? Who's an engineer? And who have I left out there? What have we got? Biologists. Oh, yeah, they do exist. Yeah, I mean, sorry, that was very neat. That wasn't great. Yeah, that was great actually. But I mean, so each of you though has your own sort of space that you're working in, right? You have your own data that you need to model. And if you're a biologist, so we go to that example first, you'll be looking at some sort of protein or whatever, some sort of drug candidate that might want to go with it, and there's ways of relating all of the forces, things that are there. If on the other hand you're doing quantum mechanics, you'll just have some ridiculously large sparse matrix that you're doing some sort of operations on. And there'll be some point in between where your data might have similar aspects. So again, there are some common things that are across all of these fields. Matrices and vectors and all those sort of things are there, and therefore you have all of your optimized libraries for doing your linear algebra activities. And similarly, everybody will have to do I/O, right? Everyone will have to read in some stuff off disk and get it into their application. Then how you actually do what you do with the data, today, for today's purposes, I really don't care what you do with the data. Everybody has this sort of issue of getting it from a linear structure of disk into a more complicated thing. So when we want to go to look at parallel I/O, there's a couple of things we want to do. Why do we want to go to parallel I/O? What are certain of the aspects of it we want to retain? So what we want to have is a situation where we have in parallel I/O a large number of clients and a large number of servers. So if we draw a large number of clients here, some sort of network that they're all plugged into, and then off the back here, some number of servers, and then each of them has some sort of disk system attached to the back of it. And you might have a situation where all the disks are, the disks might appear on multiple servers or something like that. But this is sort of our general model that we want to have. And what you want to have is a situation where you can use as much of the I/O capabilities of these machines, to get data in. So if you have lots of clients, then you want all of them to be able to read data at the same time and get a reasonable set of performance. But at the same time, you don't want this side here to be completely swamped. Because if you have too many requests coming in here and these start being slow on the requests, or they just start dropping requests because the network gets overloaded or something like that, then you have all sorts of problems that your application will go, oh, I didn't get a read, what do I do? Do I re-request the read? Do I just cancel? And an MPI, the biggest problem with MPI is that there's no real fault tolerance built into it. They talked in MPI 3 about bringing in various things of fault tolerance, but if you're still programming to MPI 1 or MPI 2 standards, everyone should be at least up to MPI 2, I guess. This has been here for maybe 20 years. But the only thing that you can do in MPI really when you find an error is you just report. So everybody, has everybody, here's another question, written code that has MPI import somewhere as an error, if something goes wrong, call MPI import. Right? Nearly everyone should have done that at some point. And that's the only way out. If you've got a problem like, if you've got a numerical problem, like you try and do a divide by 0 or something, and then you generate a floating point error, things like that. That's different, right? But if you have an MPI problem where, if I do an MPI send and it just goes wrong, or I try and do a gather and it goes wrong, or I do a read or a write and it goes wrong, the only way out is at this point is to call a report, because there's no way to sort of roll back state and say, right, can everybody go back to the previous barrier and then we'll try and pick it up again and recover. The only thing you can do is bail out. And the problem with bailing out when you're doing very large scale compute is, it takes a lot of resources to get, like if you're running on tens of thousands of cores, you might have waited for 3 days in a queue before you've been given those resources. And then you've been running on this code for 3 or 4 hours or maybe a day or 2. And then you have an error and all you can do is abort and therefore lose the 3 or 4 days of waiting time and lose the couple of days of compute time that you've been given. So no, it's bad. And so you want to make sure that you're not doing something, that the system isn't doing something that makes you end up having to call these sort of abort things. The next thing you want to do is you want to limit the number of files you want to manage. Because there's a great temptation when you initially go to parallel I/O of saying, well, look, get every MPI task to write to its own file. Because then that's straightforward and clear, because task 0 writes the file, output.0, and then MPI rank 1 writes to output.1, and rank 2 writes to output.2. Okay, so have people tried doing that at some point in their career so far? Maybe not. Yeah, okay, so some people have. And that's fine when you're running on 8 or 16 cores, because that's a manageable number of files to have. But if you scale that to tens of thousands of cores, then all of a sudden you have tens of thousands of files
most likely all sitting in one single directory. And if there's anything that a file system hates, it's lots of files in one directory. Because anytime you touch any file in the directory, you have to touch the directory structure as well. And to touch the directory structure, you have to parse all of the file metadata, update all of that, and that's just a slow operation. And so every time you want to do anything with one file, you have to look and scan through everything in another file. So that's a big slowdown on your execution. So we want to limit the number of files we're actually managing. And so if we can do some sort of way of allowing all of these different clients that are here to write through to a single file or to at least a small number of files for different parts of their node, then at least you'll have a manageable number of files. And the other thing that's nice about having a manageable number of files is when I'm finished running on this cluster and I want to then run a next simulation on some other cluster, I don't have to go, crap, now I have to force sync across 20,000 files. I have to take these 4 files and then I just start up my job again. And the other benefit that comes from that is if you've got a situation where you're writing one file per core, and let's say you run MPI run minus n 1,000, so you get 1,000 files, and then you go on to the next cluster you want to run on, and it only has 600 cores available to you, then what do? You go MPI run minus n 600, so the first 600 tasks meet the first 600 files, and then you've got 400 files left over going, who's going to read the data from those files? So if your model is 1 file per core, then you're kind of restricting yourself to only being able to run subsequent jobs on exactly the same core count as well. Where if you use some of these parallel I/O techniques of aggregating everything to one file, if your number of cores change, then on the fly, you can then just change how you're dividing up the file and reading from your file based on the number of processes that you have. And so therefore, all of the data still gets read in a sensible way. One of the things we want to do is, yes, that's sort of the portability side of things in a way. And the other thing is also we want to avoid, we want to try and do as much of the I/O here, putting it all into one location, because you don't want to have lots of small files and having to aggregate them in post-processing, because sometimes the data sets can be too big. If I'm running a large calculation for a long period of time, and then I have loads of data at the end of it, I don't want to be spending time going, ooh, cat this file and then cat that file and merge them together, or trying to load them up into some sort of editor or some other program to modify, because that just ends up being too complicated to handle. So what we want to talk about really today is about some of the areas in this sort of schematic we have of how I/O works from a parallel computing point of view. And there are, sort of every good computer science lecture has one of these sort of block diagrams. You can't help yourself. I'm a computer scientist, by the way. I'm not a scientist, so that's why I say I don't care what you do with your data once it goes in. But this is what I love, because it makes it very clear that there are layers of abstraction where each layer is responsible for its own bit and then just passes the information on to the next layer. So at the very bottom you have I/O hardware, and that's only going to be concerned with where are the ones and zeros on the disk, and how do I load them up, and how do I put them onto a network or something like that. So that's the very basic level. Then on top of that, you have a parallel file system. And the point of the parallel file system is to maintain a consistent namespace across and efficient access to this data in a reasonable manner. And this is where we're going to spend a fair bit of time this morning talking about these sort of systems here, about parallel file systems. And the thing we mean about a consistent namespace is when we have this situation here where we have lots of servers and lots of disks hanging off them. In a traditional environment, you would have a situation where you have one server, so you have I/O number 1, and then sort of if you look at NFS sort of terminology, you might have I/O1 has a /D1 for disk 1, and then also a /D2 for disk 2, and then I/O server number 2 would have a D1 and a D2. And so if you wrote something here, you could have, you could have /D2/foo here on this one. You could also /D2/foo here. And then it's a question about which foo am I referring to on disk 2? Oh, it's the one that's on I/O1 or I/O2. What we want to do is we want to be able to come up with a situation where we merge all these together into one sort of super file system and call it we'll call it /foo. We'll call it /something, it doesn't matter what it's called. But what I want to do is be able to aggregate all of the I/O to this to provide one single namespace and one single hierarchical file structure like we have over the other side across all of these different machines in a consistent and stable way. And there are lots of options that you can use for doing this. GPFS is my favorite because it's the one that I've been using for the longest. It's a proprietary system from IBM, their general parallel file system. And there's a system called Lustre, which is mostly open source, but it's been opened and closed over time as the technology has been bought by all sorts of different companies that I've lost track of who owns it at this stage. But it started in Carnegie Mellon, and then it was one of these things that went in and out of Oracle, and various people as different companies were bought and then bits were sold off. And so I actually have no idea where it is. And or there's PDFS, Parallel Virtual File System, which is PDFS is actually quite interesting in that it's quite different from a lot of other file systems in that for it to run most efficiently, you have to actually modify your application layer to talk to it almost directly. You sort of skip a lot of these layers. The thing that's nice about these sort of file systems is you have all these other layers in the middle, so this just looks like a normal file system at this point. It performs quite well because it has lots of backend, there's lots of I/O capabilities. But at the end of the day, you can still go LS and CD and all the things that you might want to do on a normal file system. Where PDFS, that really doesn't happen as much. You kind of have to program against PDFS. Moving one step up above the file system, you have this I/O forwarding layer. And that doesn't exist in an awful lot of systems. It's generally in very large systems. It provides bridges between your applications and your storage systems, so sort of to aggregate these sort of things. So if you're running on a BlueJean, you might come across the COID service, CIOD is different. CIOD on BlueJeans, or this IOFSL system that comes out of Argonne, where they try and have a consistent view, but it's only if you're scaling on very large systems to see these forwarders, whether it's effectively you go, for these 20 or for these 100 clients, send all of your I/O to this point. That I/O will then all be aggregated in some sensible way, and then just the I/O servers will then actually talk to the disk server. So you're kind of not having hundreds of thousands of clients doing I/O together. You're having them batched together into sort of hundreds at a time into one point, and then those one points going out to the very end. But that's only on very large systems. Then you have this notion of the I/O middleware, and that's where we're also going to spend a fair bit of time today, and particularly this afternoon. What it does is it allows you to coordinate your access to your storage system from multiple processes at the same time. So this is our MPI/I/O there, where we'll be able to do things like on different cores, all open the same file, all write to different parts of the file, all have different parts of the file exposed to us at the same time, so we only see our own data and all that kind of stuff. That's all handled in this middleware layer in MPI/I/O. Then above that, there is this high-level I/O libraries, things like NetCDF and HDF5, which basically provide an application level of abstraction of data to a storage. It does sort of the translate. It tries to keep things as high level as possible, so it keeps as much of the structure and the metadata about your data stored with the data as it already exists. We're not really going to. We're just going to mention that they exist, and we're not really going to go into details how to use them here. They are really quite powerful, though. So if you're going to be doing some sort of heavy-duty programming in the future, definitely have a look at HDF. I mean, that CDF is kind of being wound down now, and is sort of being merged, or the effort is being sort of put into HDF5 now, that everybody's kind of working in that space. Well, basically, it's and the thing that's nice about HDF5 is that it works in serial or in parallel. So even if you have a serial piece of code that just runs on one core, you can still use HDF5 to model your data such that it retains a certain amount of its semantic meaning. But we're not really going to talk about that. And then at the very top, you have your application where you're doing your for loops and whatever. And then at some point, you make a call that goes, well, let's say if we're going to skip the HDF5 ones, you'll do something that goes MPI_file_read, and therefore that will come down into this MPI/I/O layer. The MPI/I/O layer, assuming again we are on a smaller system to run a forwarding, will say, well, that turns into a read in onto the file system. So that'll make a GPFS call. The GPFS call will go, I wonder, it'll look to its file system structure and go, oh, that's where those things are in the physical hardware. And then the file system say, dear spinning disk, give me the data of this block. And then the block will return the data to the file system will return it back to MPI/I/O, and MPI/I/O will give it to the relevant task, the MPI task that asks for the data. So you have this sort of model of, data requests go down, data comes back up. or if you're doing a write, the data comes down and then an acknowledgement comes back up to say yes, all of the layers have completed whatever they're meant to do. So that's really what, and so the things we're really going to look at today are going to be this layer here and this layer here, okay? Just so everybody's clear where. And why do we want to do all of these things? It's because of this, right? As HPC people, you've all seen something that looks somewhat like this, where you have this notion of if data is right beside your CPU, it's super fast. So, you know, in a couple of clock cycles, you can get data out of your level 1 cache that's on your CPU. But if you have to go out to disk, you know, even if you're writing to flash data, to flash disk, you know, it's still, orders of magnitude bigger. So in this case, you're about from 1 nanosecond up to 50 microseconds. So that's what 5,000 times slower to do a read from a flash disk than it is to do it from the register. And if you actually have to go all the way out to a hard disk, you know, it's of the order of a number of milliseconds. And if you have to go to tape, well, then forget about it, right? It's you know, you are in the order of seconds to minutes. So it's, you know, but the flip side of it is, as you get worse performance, you know, you get much more capacity available to you, and so there is this balancing thing of, you know, how do, are there situations where the data should be moved up or down in this hierarchy to where it's the most appropriate place? What we're trying to do is we're trying to come up with schemes that allow us to at least try and hide some of this latency from the end user as a programmer, while also taking advantage of the capacity things that are here. So you could argue, why don't we look at actually, no, this is before we go on to that. Just to note that even though as we're increasing, as time is going on, Moore's law is still very much in play in the storage side of things. In the CPU side of things, we can kind of say, we're not getting faster chips anymore. We're just getting more and more cores on chip. So we're still shrinking the size of transistors or whatever. But in disk size, we're just still increasing capacity and increasing performance. So over the last decade or so, we've kind of gone up a factor of 10 in terms of the amount of capacity in a normal size disk. So if you go down to any shop these days, you can easily go in and buy a 3 or a 4 terabyte disk, and it's €100 or something like that. It's not that expensive. And the speed of those disks has increased somewhat as well. So we're still making progress on that. But the capacity is increasing still faster than the access speed is. So if you want to write all of the data to a disk, it takes longer now to fill an entire disk than it did last year. And it took longer last year than it did the year before. So, when we're in these sort of situations of writing to disks, we have to bear in mind that the write speed is still quite slow relative to the speed of access of data that we want to have it through the CPU level. So the question then is, why don't we put everything at the top of the pyramid? Why isn't everything just made out of L1 or L2 cache? And sure, wouldn't that be great? And the reason is cost, right? And there's always a downside. There just isn't enough capacity in all of the fabrication plants on the planet to come anywhere near building enough silicon to replace all of the magnetic capacity that's in disks and tapes. The global capacity for making disks is somewhere of the order of 500 million disks a year. It's that sort of space. And let's say that 2 terabyte disks each gets us to somewhere, around 1 zettabyte of storage every year is being manufactured somewhere as across the world in total. The flip side of that is in all of the chip fabrication plants, there's somewhere of the order again of about 500,000 wafers being made every year. So are people familiar with how chips are made? Generally, sort of basically they have these huge big sort of 4 meter, I can't reach 4 meters, I'm going to go 2 meters. It's it's larger than you can reach. Big huge circular wafers that they basically spend a month dipping in various layers of liquids, and then as they set, then they etch the next layer of the chip in, and then they dip it again, and then they etch another layer, and then they make effectively all of the various connections and the transistors that they need to make the chip work. But anyway, these wafers are quite large, and when you've made a wafer, as you're in Intel or AMD's fabrication plant, they make lots of these chips on a single wafer and then just slice them up and then they stick them on some packaging to actually make them work. But there's of the order of about 4 terabytes worth of DRAM or SRAM, I should say, for registers and caches for each of the chips on each wafer. So there's about 4 terabytes. So if you look at each individual chip has, maybe a couple of megs of cache, and then you're kind of saying there's about 3,000 or 4,000 chips, up to that on a particular wafer. Then you get to this sort of figure out about 4 terabytes per wafer. So if you multiply this out, you get about 2 exabytes. And so we're 500 times the difference in production of this versus this. So there's just no way that you can't get away from using disks. And again, it comes down to this cost side of normal spinning disks cost about €40 per terabyte. That's pretty cheap. You go down, buy your 3 terabyte disk for about €100, give or take. But if you want to do that in solids, in flash drives, it's somewhere of the order of about €500 per terabyte if you want to buy large disks. And if you were to do that in DRAM and try and scale it up, it's about €10,000 per terabyte. But you can't buy €10,000 worth of RAM. You can't buy a terabyte of L2 cache for your chip. Right? It just doesn't work that way, because that would just be crazy. But that's if you sort of take the price of a chip and then take the amount of DRAM DRAM that's on. That's what the Why was it DRAM? The amount of SRAM that's on a particular chip. It's that sort of pricing model. So that's the main reason why we can't just make everything out of SRAM. And the other thing is tape is still a player, even though we sort of mock us and say, look, it's it's superly slow and it's it's superly whatever. It still has large benefits for data sets that you need occasionally, but that do need long-term storage. Then tape is perfect, and tape has huge benefits. It's about half the price of hard disks and requires no maintenance. It doesn't need to, there's no power consumption for a tape when it's sitting on a shelf. Its life is longer than a hard disk because it has less mechanical action. And then when you need the data on it, what you do is you just load it into your tape player and you get it up in advance. And then you copy it off the tape onto, at least onto a system somewhere in this sort of level. So even though you won't go raw to this and say, now that from an MPIO layer, please access tape. But what you'll say is in advance, you say, right, I know I'm going to do this calculation next week. So this week, why don't I get my tapes lined up, load all my data off, at least get them onto disk somewhere. And then when I get to run my job, then my data will be here. And then when I'm finished, I can say, right, now put it all back out to tape because I don't need it now for another year or whatever it is that I need to do. So tape is still very much a player in this space for delivering things. So when we've had that discussion about why things are the way they are in terms of storage devices, what we need to think of is what's the purpose of a file system. So we've kind of already said this. We need to maintain a consistent namespace, and we need to store the file contents, so the bits, the ones and zeros of your actual data, and we need to store the metadata about this file. So the metadata about it is like who owns it, what are the permissions for it, when's the last time it was accessed, all that kind of metadata. The metadata has become the word of choice these days. From all of the Edward Snowden related things and people spying on things. Oh, I wasn't listening to your phone call. I just have all the metadata about everybody who you were phoning all the time. So therefore, I actually know that you're a terrorist without actually having to listen to your phone calls. Now, so metadata is actually quite important. If you had this conversation with somebody 10 years ago, metadata doesn't know what metadata is, but everybody now knows what metadata is. So that's good. It's a one upside of spawning schemes. But that's consistent across all file systems, whether it's on a local, whether it's a parallel, whether it's a network file system. When you introduce a network, you add an additional problem in that you have to be able to coordinate all of this access between all of our clients at the same time, giving reasonable performance, trying to aggregate at the back end when we go to these parallel file systems. So we're adding more complexity as we're going along here. There's a sort of, one of these sort of, it's not really a saying, that's overstating it, but there's sort of an observation of building a file system is about 10% of your effort if you're going to write a parallel file system will go into actually how do I get data from a disk and how do I coordinate all of my data, sort of how do I provide a consistent database. And the other 90% of your effort will be putting in tools and systems to work around problems. So to build in fault tolerance, to build in some sort of scalability, all those things, all of that effort. The actual engineering work that goes into, if you had a parallel file system that had no users, it would be really easy to write it. The problem is real users are messy, cause problems, and therefore you need to be able to support the sort of crazy things that they want to do. And so the effort in actually writing parallel file system isn't so much writing a file system, it's writing all the support infrastructure that goes around it to make it robust and maintainable. So you need to be able to do high performance I/O, so you need to be able to talk to your fast networks. You need to be able to have multiple concurrent client access, so each of your different people at the top of the network diagram over there are able to talk to each of the different people at the bottom all at the same time in sort of out of order things. The other thing that to keep in mind about parallel file systems, we're not going to talk about it really at all today, apart from saying here, you have issues of trying to keep things in sync. Because there's no notion of global time. Like, there's no thing that says that time is now 12 o'clock on the button. Because each computer will be slightly different from each other. There'll be, you know, delays of time. You can try, and so there are protocols like NTP that try and synchronize machines to be all kind of the same, but not down to the level of sort of at the nanosecond level of everybody thinks the time is exactly the same. If you're within you know, certainly a couple of, you know, tens of microseconds of each other, that's close enough. But in parallel file systems, that can be a problem when all of a sudden you have two people trying to write to the same thing at the same time. They both think that their time is right, and the application has decided this has happened after this, therefore this should be the one that gets written because this one should have been overwritten. But by the time they get to the file system, they've come in a slightly different order, and how do you keep all of that synchronization happening? So there's all those sort of problems that crop up, and we're kind of going to arm wave our way through these things. In a local file system, on a single machine, or, you know, sort of like my laptop here, you know, what we have is we have this sort of structure of, we have a super block that sits at the top of the disk that says this is in this case here, it's some sort of UFS type file system in a Mac, but it could be an ext4 file system in a Linux machine, or it could be an NTFS if you're running Windows, or whatever it's going to be. So there are lots of different file systems, but they all follow roughly the same sort of structure, where you have a super block that tells you what sort of file system it is and where all the other stuff is. That then passes out to a binary tree that's written onto this that has all of the, you know, copies of the super block and additional information around, you know, where to go next for your actual metadata as a block list in your inodes. And then within your block list, you can go directly to disk, or you have indirect blocks that will give you, you know, additional capacity within a single file, and then eventually you come down to data. Okay, so you have this sort of structure on the right-hand side. And what we want to do is be able to provide a persistent view of this. So by persistent, we mean when the power goes off, it should still stay there, and then when you turn the power back on, it should still be there again. As opposed to, and that's the thing about, you know, why we use the term dynamic RAM or DRAM. And, you know, if we're talking about RAM, is, you know, let's stop the thing off. When the power goes, the data disappears, and then, you know, you boot it up again, it's not there anymore unless it's got some sort of battery power supply that's keeping it charged over time. Where persistent means it survives over a power, not necessarily power failure, but if there's an interruption in service, that your data is still there when you come back to it in the future. And so it has a persistent view of this data that has all of the ones and zeros of your data plus all of the metadata. And so early, you know, research into that I think has been auto-corrected from something else I wanted to say. Why do I write differentiation? That's a really weird word to write. I'm trying to develop. But anyway, early research and development was also kind of optimizing access on a single device. So, you know, people didn't really have to worry about parallel things because they weren't doing parallel things here. And so there are, you know, lots of people gone down different routes of generating all of these different their serial single local file systems. All of them have their own benefits, all of them have their own features that people like. And it's a matter of choice. You know, when you install a new Linux machine, you will get given the choice of, do you want to format your disk as ext4, which is kind of the default, but you could choose to use ZFS or XFS or RiserFS or, you know, any of these sort of, you know, there are lots of them that are out there, and they all follow roughly the same structure. They all tackle things in slightly different ways, but they all kind of get it. When you want to go beyond a single file system on a single disk, then you have to start to scale up. And this is where it comes in. So we have several levels at which we can undertake this scaling operation. Firstly, on the disk level, within the single system, we can employ what are called RAID groups. And what RAID groups are, not really go into much detail, but basically, if you have, you know, lots of disks all on a single machine, what you can do is you can group them together in some way. and then provide effectively a virtual interface that when the data comes in, a bit of it will be written here, a bit of it will be written here, a bit of it will be written here, a bit of it will be written here. There are different grade groups and different grade levels, which we won't really go into. They're all called RAID 0, RAID 1, RAID 5, RAID 6, RAID 10, and they're all defined to mean different things. But basically what they do is they allow us a way of taking multiple disks and making them appear as if they're a single supersized disk. So if I have lots of 1 terabyte disks, 1 TB, and 1 TB, and I put these together into a RAID 0, which is just striping the data together, I end up with a single file system that is 4 terabytes in size. So that's pretty nice, because now I don't have to buy a 4 terabyte disk, I have to buy 4 1 terabyte disks, which might be cheaper. Well, actually, these days are probably won't. But what we'll certainly then do is buy 4 3 terabyte disks and have a 12 terabyte virtual file system that I can then work on. There are also things built into RAID to allow us to do things like redundancy and recovery. So I might say, let's use these as my data disks and then put a parity of all of the bits on this. So a bit gets written here, a bit gets written here, a bit gets written here. And then I take some sort of parity check of all of these and write the parity bit out here. So it means that if one of these fails, I can at least still recover the data. Because the thing to observe is, as you start, a disk is unreliable. Lots of disks are really unreliable, okay? And so when you scale up to very large parallel file systems, if you go to one of the big HPC centers, they're going to be changing out disks on a daily or at least on a weekly basis because disks just fail. But what you can do is you can build your fault tolerance into your system such that it allows you to not have to worry about any individual disk or any few disks scattered around the place randomly failing. You can replace them before you've had two. And this is RAID 5 effectively, where you have a number of disks and one parity. So if you have one failure, you can still recover. But if you lose 2 disks, then you're dead. Because now all of a sudden you are missing too many bits of information to recover back your other information. So RAID 6, what it does is it just adds a different parity calculation, and so therefore it allows you to still recover because you have one piece of original data and 2 orthogonally different parity information that will allow you to recover these 2 other bits of information here. So that's what I'm mean by RAID. But that's still within a single group. Then you have this sort of situation of whether I use SAN or NAS, and SAN is just more expensive. Right? That's really the bottom line. SAN will run faster, but will be more expensive than network attached storage. Network attached storage is literally you have a server with a disk in it, and the server runs some sort of piece of software like an NFS client or an iSCSI client or whatever, but it's basically over Ethernet or something like that. Where SAN is generally over fiber channel or over InfiniBand, is much faster, but is much more expensive. So you go to something like EMC or NetApp or DDN or something like that, they'll sell you a very fancy SAN backend. If you go to somebody like Isilon or you go to Dell, and they'll sell you their MG3000 series of things. They're in the NAS space and they're just network attached, but they're all the same. Effectively, from a logical point of view, they kind of give you the same way of basically exposing disks onto a network somewhere. And then when we move to a distributed file system, what we want to do is we want to take all of this, all of these things that have been exposed either through SAN or through NAS, and virtualize them in the sense of we want to be able to put a virtual layer above all of that everybody, when they talk to it, don't see where the data ends up. So when I do a write to my distributed file system, I don't want to know or have to care whether it goes to this server over here, or comes down and goes into a server over here, or comes straight through into, or we're actually getting split up and written onto 7 different servers at the same time. And then whether those 7 servers actually then write them onto 100 disks or onto 1 disk, I never want to care. All I want to know is me as an application, I'm writing to a file system, and then the file system kind of hides all of that distance away from me. Well, when we start scaling it up, the problems then crop up of how do we coordinate this, or how do we lock in synchronization? If I have 2 people trying to write to the same directory, how do I coordinate who gets to update the directory object first? Or if they're writing to a file, who gets to write first, and all that kind of stuff. And then also fault tolerance, so then you want to avoid single points of failure, so that's why we have redundant disks. Then within the file system, we might also have some level of redundancy. In our network, we might have different levels of redundancy, so a standard sort of setup for a parallel file system might be, you have, let's just try to have loads of disks somewhere, right? And then you have a couple of I/O servers, and each of them can see all of the disks, so they're cross-mounted with, say, a fiber channel, And then they also then have, in the network, you have multiple connections to switches from each of the I/O servers, and then all the clients sort of hang off here. So you've no single point of failure. I can come down here, I can go from, whether your clients might or might not be fault tolerant, right? But assuming that your clients are always going to be okay, these level switches are okay. Once your data gets to here, it can go this path through this server, then to here to get to the disk, or it can go this one to this server to get to the disk, or you can go to this one and then down here. So you've got multiple paths through the thing. You can probably also have a network that allows you to also route sort of across this way down here, if this cable breaks, all those sort of things. So you build in multiple levels of fault tolerance to work around problems and avoid this situation where you've got single points of failure. But these are some of the problems that crop up when we have these large-scale systems. We've kind of mentioned them all already. Who owns the locks? Who can update the directories? Who can read the stuff? It's not necessarily easy. If you run ls-l, and again we said with lots of files in it, there's a lot of reading that needs to be done, a lot of digging out of information. And then similarly, how do you know, if we're both writing or reading to a file at the same time, can I write something while somebody else is reading? If they have some sort of optimization, read ahead, so they're preempting what the user is going to want to end up doing, can I survive this? And so there are lots of these parallel file systems out there that approach a lot of these things. They all take them from slightly different angles to solve slightly different issues. Their pet peeve with the thing. Here are some of them. A few of them are more open source than others. Storage is still one of these places where vendors still have a lot of sway, because they're the ones who are generally only the ones who are willing to put in the time and effort. But certainly PDFS and SEP are entirely open source. ISON and Panasas, you have to buy their actual devices, but then they have some of these things put on. And then, as we mentioned already, Lustre and GPFS. So this is what a parallel file system looks like. This is the same as we have to draw this on the blackboard. But this is effectively a summary of where we've been up to so far. In my file system, I might have a file called hello.c that's in /home/dfrost/hello.c. It's a very large hello world program. It takes 3 blocks on disk, so it's 3K of size. I must have written an awful lot of rubbish or an awful lot of comments in the file, something like that. But the point is, where this lives on disk, in my file system, my application goes /home/dfrost/hello.c, and then it starts reading from it. But when a client actually starts to read from that, it goes across the network and talks to these I/O servers and finds that, as it wants to parse its way through the file system, it has to talk to this guy to find out where the entry for /home is. That will tell them where to look for, /dfrost is, and then in /dfrost there'll be an entry here that says there's a file called hello.c, and each of its blocks are located on a disk on IO4, on IO2, and IO3. So when I try to read that, the file system here at this sort of virtual level says, give them this block first from IO4, and then give them this block here from IO2, and then give them IO3 at the very end. And all of that is hidden away from me as the user. I just do an F open, a read, and an F close. And the file system handles all of the issues of concurrency and synchronization and fault tolerance and all that kind of stuff is hidden away from me. So this is the point, is the data can be striped across all of these locations. If we talk a little bit about GPFS for a second, GPFS is the file system that I have most faith in terms of building parallel file systems. And its data path is pretty much exactly sort of set there. There are servers that have disks associated with them. They create these NSDs, and the NSDs can be shared between multiple devices. So actually, the disk that has this stuff on it here might actually be also cross-mounted on one or more of these other I/O servers here. They have it's a block-oriented file system. So when a client wants to do some reading or writing, it just says, give me a list of blocks that I'm allowed to read or write to, and then they write them, and then the client writes them back over the network in a certain length of time, and then they get distributed across all of the different I/O servers, and that's all controlled by the I/O servers themselves. The clients just kind of talk to whoever they're told to talk to. And it's tuned that it can run over things like InfiniBand natively, so you can get very high performance RDMA access, or it can run over normal TCP/IP networks as well. So if you just have a group of workstations, you can still install GPFS and get all of these to work. And it has full POSIX compliance. The POSIX being the Unix standard for what a file system should look like, so you can do LS, CD, CHO, and CHMOD, all those sort of things that you would ever have written on. Lustre is organized slightly differently in that the storage and the metadata is actually separated in Lustre. So anytime you make a request to do an LS or something, you talk to the metadata server. And then the metadata server will give you back the metadata, and then you go, okay, the metadata is telling me that this data is on that server, on that server, on that server. So then my client will then make 3 requests to each of the 3 IOs, the object storage servers, and we'll get the data back from each of these. The OSTs themselves that are on the storage servers are actually built on top of a local file system such as ext4 or Btrfs, usually are the 2 that are recommended, and the block allocation is handled at that lower level. So Lustre is much more parallel on a file level, where GPFS is much more block oriented. And that's just one of these design decisions that was made at the very start of the development of each of these things. They both went, what way are we going to lay out our file system? GPFS guys went, we want a block level thing. Lustre went, we want a file level thing. And then everything else follows from that. Well, then we have to organize our data this way. Again, the client's going to make a POSIX file system, so you can do your LSs and all that if you need to. And again, it runs over TCP and how. So you can see a lot of them are the same, but under the hood, all of this is very different. But from you as the application user, you still end up seeing a POSIX file system that runs in a scalable way. So when we're doing our parallel I/O, there are a number of patterns that we fall into. Okay, in each of these, the round ones are meant to be sort of MPI tasks. And then the green ones, the green sort of square ones, are meant to be, where my I/O is going. And so we have this traditional sort of method of serial I/O, where what we do is we say, let rank 0 do all the work. So we do calculations, and then at some point, we issue an MPI gather or MPI reduce, and everything goes to rank 0, and then rank 0 opens a file and spits out some data, and then saves it, and then it's done. Okay? I think pretty much everybody has written that at some point, right? That is when you start writing parallel programs, that's what you do. And it's the same, not even when we're talking about I/O, but in terms of doing everything, how much of your code has a line that says, if rank equals 0, do something, right? Doesn't matter what. Your first MPI programs are filled with this kind of stuff. Like, that's just the way we all work. Right? It's just, there's nothing wrong with that, except it doesn't scale. Okay, that's the biggest problem with it, is that it doesn't scale. Because at 4, that's fine. But if you've got 4,000 and all of a sudden they're all spitting all their data onto rank 0, and then rank 0 is trying to do a single write, nothing will ever work, because you'll have a situation where I have all of the data is going across the network and then into rank 0 here, and then it's trying to sort of squeeze the data out here, and so you're not taking advantage of all of this performance that's available to you at the back end. And I'm actually oversaturating this thing, because they're all trying to reduce or gather or whatever it's going to be to this point, and then he's trying to do all of the data. So this is the second model, and this is the one we kind of mentioned already, of the one file per MPI task, and that kind of works better than the first one, in that at least you're now able to say, well, rank 0 is writing some stuff, and rank 1 is writing stuff, and rank 2 and rank all the way up to rank n are all writing stuff at the same time. Therefore, you're taking advantage of the performance of the network, and you're taking advantage of the performance of the aggregated disk systems and all that kind of stuff at the back. But you have this portability problem, as we said, of if I run on 10 nodes now and then I run on 100 the next time, how do I decide how I redivide up my data and all that kind of stuff? So this is sort of the holy grail. What we want to end up doing is a situation where all of our MPI tasks are doing shared file parallel I/O. So they're taking advantage, they're all doing their own I/O, but to a shared file in a structured and organized way. You don't want to, because if all of these just do F open and then do, actually, here's the question: how many people are Fortran programmers? How many people are C programmers? How many people? What else is there? Nobody does anything else. Or C++. Okay, so C and C++ is the same. But like in terms of me talking about things like F open or whatever, the semantics in Fortran are kind of weird and wacky, and so I don't really know. But since you're all C and C++ people, this should at least make sense. But if everybody just did an F open, so we did an F open, and then they all do an F printf or something, that doesn't work for this. Okay, you need to do something a bit cleverer. Because if they all do an F open, they all get a file pointer that points to the beginning of the file. And then if they all go fprintf, they all write to the same block. So they all overwrite each other, and you don't actually end up getting any benefit. You need to use the MPIO tools, and then sitting it on top of a parallel file system to get you the benefit of what you want to do. We can do, if we want to implement the first version, we can just use standard standard POSIX semantics. Get a file pointer, open something, read something from it, and close it. It works. And the thing that's nice about it is, it's there. It's the lowest common denominator, but it works, right? The downside is it lacks any support to set for parallel things. So, from a POSIX.io point of view, these parallel programs appear to be, if I'm running on n ranks, they appear to be n different programs all writing different things, as opposed to being able to harness the notion that actually they're all the same thing, they're just writing different parts of the single data set. And there's no support for non-contiguous I/O, so I can't say write a bit here, and then write another bit, and then write another bit. There are strict rules about reads after writes and things like that, so you can get into out of sync problems. But for parallel I/O, we can do it for parallel applications. Please avoid it, but everybody still does it, and especially for debugging, right? How many people have written something that goes, if error state, printf got this far, printf didn't get this far, and then you kind of run it and you sort of see what comes out of the terminal screen. Right? We all do I/O that way, but it's not necessarily the best. MPI-I/O was brought in MPI-2. Which is the standard, the second iteration of the standard of MPI, which came out in the late 90s, 97, 98, I think it was. And the data model for MPI-I/O is still the same. We still talk about files, so it's a stream of bytes sitting on disk somewhere. But it has large features that are really useful. Things like collective I/O, non-contiguous, non-blocking, and it's portable. So issues around this are avoidable. So it has all the things we want to do in a parallel system. And the thing to note about MPI-O is all done using binary reads and writes. There's no conversion, so you can't, if you open it using VI or Emacs. Here's another question: how many people are VI people? And how many people are Emacs users?
You cannot go home.
Yeah, anybody who's Emacs, just get it. So look, if you VI it, it just doesn't make sense. So you have to use tools like hexdump or OG to actually examine the files in any detail, and we look at that. What I want to do is just want to finish by writing some very basic MPI things, so at least when we go up to the lab then after tea, we'll be able to do some basic things. And what I'll do is I'll stick these up on the overheads. Do we do that here on your own laptop, or should we go over to the Lloyd building actually? Or do we care? Or is there a structure to this? Well, that's Mike. But anyway, I'll put these things back up. But basically, MPI-I/O gives you a few functions that we need to talk about. There's an MPI file open, which is the equivalent of fopen, which basically is a collective operator on your communicator. So your MPI com world or whatever it goes in there. A file name of both that says whether you want to read or write to the file, and then a pointer to a file, an MPI file object. And so this is collective, so everybody does it across all of the things, and then they all have access to this single shared file. If you want to only open a file at a particular place, on a per node basis, you can use MPI com self to cheat. So effectively use the self communicator, but try not to use that. And then you can close it afterwards. And the thing that's nice about explicitly closing files, apart from its good practice, is the file value will be set to MPI file null after you've closed it. And the thing that's nice about that is then if you accidentally try and read or write to it again, you will get a segmentation fault rather than just some random garbage overwriting something that you thought was in your file. So you'll be able to detect where your problems are. In terms of reading and writing, there are MPI file read and MPI file write, and they're exactly as you imagine them to be. There's a file handle, there's a buffer where you want to put the data in, and you tell it how many MPI hints or how many MPI doubles you want to read, and then you have your normal MPI status object at the end that allows you. Like scanf and printf in the normal C library, these advance your file pointer to the file. So when you do an MPI file read, when you open a file, the file pointer points to the start of the file. And then you do a read of 10 ints. It'll move you on 40 bytes into the file, and now your file pointer will be pointing to byte number 41. And then you do 100 doubles, so that's another 800, so now we're pointing down here to 841, and so on. So the file pointer will move as you do reads and writes in these things. But you can also then manually move the file pointer around using MPI file C to tell it where you want to move to. So the offset is just a number that says I want to move 100 or 500 bytes or whatever Normally you make that up out of n times size of some data type because you want to move around. And then you have 3 places where you can seek from. So you can go seek set as seeking from the start to say I want to move 100 bytes into the file. Go, you put your offset to 100 and quent to MPI set seek. MPI seek cur will say move 100 bytes on from where I currently am. And then similarly, there's also a seek end which will allow you to seek backwards from the back of the file. So one way or the other, you should be able to find the places where you want to go. And then there is a version of these things that allow you to not clear end file pointer. We'll talk about those afterwards. So, well, we're going to have a break, and then afterwards we're going to go and try and figure out if we can get you to. We're just done. I might sneak in and tell me we have to stop. We're at the break. What we're going to try and do is we're going to set up a situation where we can write a raw data file of integers. So we're going to use fwrite or something like that to just write out a string of raw integers to disk, and then play around with these things using OD or hexdump to make sure that we have the data that we think so. And then we're going to try and open them using MPI file open and experiment then on our different MPI tasks of reading in different values from the file into different places. We'll try reading them in using offsets. We'll try reading them in moving the file pointer around the place. And the questions are, this is the very basic level, because then in the afternoon we're going to go into actually the sort of more complicated side of trying to write MPI out. But this is to get you comfortable with the idea of we have a single shared file. So when you do an ls minus l of your file, there will be one file. It'll be slash whatever slash my file. And then what you're going to do is you're going to take different parts of that and load them into different MPI tasks, possibly on different machines, using these MPI file reads and writes. And then if you can get this part cracked in the lab session for lunchtime, then we should be in a good space to actually in the afternoon to actually try and understand some of the more complicated side of MPI. So, does anybody have any questions before we go and have some coffee? No. Okay, well then let's go have a break, and then we'll figure out what we're going to do after that.
Actually, what happens we are using actually HDF1 in our thing. We're not using HDF5.
No, HDF5 is better.
Yeah, and
I also use HDF5.
Yeah,
It's also by right.
yeah, no, yeah, we have MPI right.
It's a matter of
You're getting the way to cover it. Should they have a real or not? Right now, we can just do our stuff here.
I think, yeah, let's see what the other scripts are. Yeah.
Hi.